Yeah. So I will continue with the topic, which is directly related to what I said in the morning. So we have seen that if there are two periodic oscillators with slightly maybe different frequencies, and there is some coupling between them, interaction, then if the interaction is attractive, so which wants to align them, so they eventually will oscillate for strong enough coupling with all the same frequency. And the same happens also if the interaction is repulsing. They will just be out of phase, but also will attain the same frequency. Now, we will look how this looks like if we have many of such oscillators. It will be some finite populations, but also in the so-called thermodynamic limit of infinite populations. And mainly here, there will be so-called global coupling, so that there will be no arrangement of oscillations in space, but there will be some field which is described as a mean field, which acts on all oscillators. So I probably will skip the last part to the Friday, and we'll try to represent here this part. So there are quite interesting two theories which are more or less independently introduced, and which are show that some some mysterious integrability, even or reduction in some types of populations of oscillators, and they can be used to describe such ensembles. So in physics, so there are many cases when indeed there is no some spatial arrangement of oscillators, but they can be considered as globally coupled. For example, if you have an array of electronic oscillators or Josephson junctions, there is just one current which goes through all of them. And so there is indeed, it's in the exact sense, it's mean field force. So it is not an approximation, but it's just one common field which acts on all oscillators. In biology, especially neural ensembles, there is, in fact, so each neuron has maybe 10,000 connections to other neurons. So it's indeed, it's not nearest neighbors, but indeed in the whole area they are somehow coupled. And mean field coupling or global coupling is a really good approximation. And say in social behavior, if one thinks about an applause in, say, opera, then indeed, so there is, you don't hear only your nearest neighbors, you hear almost everybody there. So indeed, global coupling will be a very good approximation. Now, and in such cases, so I will also speak about this example. So these are fireflies, so these are neurons. Indeed, synchronization can be treated as a non-equilibrium phase transition in such a large system. Now, what could be a general formulation just in abstract terms of such a global coupling if each element is a dynamical system? Now, we write for each element which has some dynamical variables, small x, with index k, some equations. They could be identical, or they could have maybe different parameters. And then we assume that there are coupling through some kind of mean fields. And we can separate these mean fields into two classes. So X are mean fields which just appear as averages of some observables over the whole population. So they are somehow algebraically related to these individual variables. And another mean fields could have their own dynamics. And they can be driven by this, so to say, algebraic mean fields. Yeah, so there are, in principle, you can distinguish two types of coupling. So for example, if you have array, electronic array, and there is current through them, so this current is this y, and for y variables, we also have some maybe equation for this current and voltage which appear in this form. Yeah. So now individual oscillators, they could be maybe periodic or chaotic, but we'll today consider only periodic ones. And then one distinguishes what is happening in such a system according to what is behavior of these mean fields. So if they are stationary, it's just static, so this typically happens if here all oscillators have different phases, and this is effective averaging, which just gives a constant. So then there is no synchronization. But if here there is some oscillation also in these mean fields, one speaks on the appearance of some collective synchronous rhythm. Yeah. So this how it could look generally. Now, how you could describe this? So if you look on the thermodynamic limit and goes to infinity, then the density of these oscillators obeys the following equation, partial differential equation, where also mean fields are coming. And these mean fields are defined by these averages. And so the problem will be of this system of, or this partial differential equation, which is nonlinear because of this, so it depends on rho itself, and plus a set of ordinary differential equations for this time-dependent mean fields. So it will be system of nonlinear integral differential equations, and it's really not easy to study, but there are some cases, even interesting cases, where you indeed can have some reduction and write more or less explicit solution of such a system. Okay. So it will be what this reduction essentially means, so that this density can be characterized with several variables, and we get a closed system of ordinary differential equations. So at first glance, it looks rather improbable, but we will see how it works in these two theories. One is due to Watanabe and Strogatz. It was developed 93, 94, and this is 2008 by Ott-Antonsen, and they are related to each other. But to apply, so these models are of restricted applicability, and I'll now introduce the famous Kuramoto model to which these two approaches can be applied. So this model is in some sense generalization of the Adler equation to many oscillators. You see, so if you just consider two oscillators, so this will be exactly the Adler equation which we wrote and derived in the first part. So without coupling, each oscillator has its own phase, its own frequency. And then there is this term, which is exactly the phase difference of these two oscillators. Sine, okay, I write sine, but maybe at some point I'll generalize it and add here some additional phase, but okay, sine is a typical function which appears here. And there is just many oscillators, and each pair is an Adler equation, and you sum them all together. So you assume that there is some superposition principle that all couplings are of this type, and here you just normalize to have a good thermodynamic limit. So you can just use trigonometrical identity and exactly rewrite this coupling term as these two sums. And you see, so these are two mean fields as algebraic mean fields. So this is one observable, average of observable cosine phi, and this is average of observable sine phi. So if we just combine these two as one complex observable, so we can write this model as just as each oscillator has its own frequency, and it is driven by the mean field Z, and mean field has this form, and it is just sum of complex fields or complex observables from each oscillator. Yeah? So summarizing, so many oscillators are described by their phases, and for their interaction we assume the simplest Adler equation, which results in this Kuramoto model. So, and Z, so essentially Z is the parameter which says you how strong is interaction, and if it says you all you need for the distribution of these phases. And there are two main cases. So if, sorry. Now, you have to assume additionally something about these frequencies. And the typical assumption is that they are not identical, but they are somehow distributed in some range. Yeah, so this is, so all omegas are not the same, but have some distribution. And the width of this distribution is analogous to temperature in the, standard statistical mechanics, because it is gives you the, some level of disorder in this system. So if the coupling is small, so then there is no synchronization, and all the phases rotate, so mean field is 0, so each oscillator rotates with its own frequency, and they are uniformly distributed on the circle. And so this is state without synchronization. But for large epsilon, so the synchronization appears, and so there is some field, and in this field, phases are distributed here. They have maximum, and this field is this distribution maintains this mean field, and there is synchronous state. So this is how this synchronization transition looks like. So the width of the distribution plays a role of some temperature in quotation mark, although it is a static disorder. There is no any fluctuations here. And this is how this transition looks like. Z is coming back, is this quantity. It's a mean field, complex mean field, and it's exactly the forcing on each oscillator. It's like magnetization. You see, if you think about classical theory of ferromagnetism, so you have, so your oscillators are spins, and Z is the magnetization, and magnetization makes spins aligned with it. And if your temperature is too high, it cannot maintain, and magnetization is 0. And here, there is no temperature, there is no spins, but there are phases, and their interaction, and this Z plays a role of this magnetization. The Z is called Kuramoto order parameter. So it is complex order parameter. Yeah, it's called Kuramoto order parameter. So maybe it is a good idea at this point to present how it does look like an experiment. Okay, so maybe I first show you two small. Okay, so now maybe two videos are more related to the first part, when I said that two oscillators can synchronize. So the most easy experiment you can do yourself and also find a lot of internet is the experiment with metronomes. So I just maybe not show it fully. So you start two metronomes, you put it on the plate. It's two cans, and you see they have different frequencies. But at some moment, after some interaction and transitional period, they start to be in phase, and they remain in this situation, in the synchronized situation, for the next time. But you can change this coupling and make it repulsive, so you will see this situation. You see, so the same cans, but on some ribbon placed. And you see this changes coupling, and from attractive, it becomes repulsive. And they become out of phase. It's just form. Now you see coupling somehow depends on the eigenfrequency of this support. So if you write equations, and you write it is like a one damped oscillator, this support, it depends on the eigenfrequency of it. But you see, so now it is another state. Yeah. Sorry? Because I know the result, only from this. I don't know exact form of interaction, but I know the result. The result is here, so I conclude that it is repulsive. Now, so there was, now I see if you was so. Now, the next video is in fact was produced in our lab, but it was more by professional. You will see, so it is done professionally. There was, you know, so there is German-French channel Arte. And there was some team which wanted to produce for this channel some documentary, 1 hour documentary about applause, with different funny stories about how a politician makes a speech in parliament, and then people start applauding him, and then he comes to his place and start applauding himself too, and many such things. And they heard that, okay, so the physicists also know something about applause, so that in applause you can synchronize. And they made this short video, how many metronomes can synchronize. You had a question? No. You can do yourself. Yeah. So you just buy each metronome is some 20 euros. Cans, you need, so people say so that only Coca-Cola cans, Pepsi will not work. And then you just make experiment yourself. So it's, okay, I don't know really. So it's just YouTube demonstration. But you can do this with many. So it's Misha Rosenblum, Markus Abel. So I was on some on leave, so they did it. And you start them just randomly. You see, so, and then after some time, so some are out of phase still, but majority is, yeah. Okay, so this is just a hand-on experiment. Now, there is you can do this with really very sophisticated modern objects. So you can have, you know, there is such synthetic biology where you put a genetic circuit with desirable behavior into cells and you can observe it. So you can create a clock of genetic oscillator, which maybe one period is maybe 1 hour or 30 minutes. You put it in cells, and on some time, on some phase of these clocks, or of this periodicity, they fluoresce, and so you observe this periodicity in living cells. Now you put many cells in, so here it will be different compartments. Experiment was done in the lab of Jeff Hastie and Lev Zimring at San Diego. And they first, and they are coupled through some chemical which is in gaseous phase. So there is more or less global coupling between these thousands and maybe millions of cells which are oscillating. And you will see these oscillations in the next movie, so how they synchronize. First they were asynchronous, and then quite soon they all, you see, so in this compartment, it's not one cell, but it's maybe 1,000 of cells, E. coli, which live there, and they, so this is the characteristic time, and they all like artificial fireflies. Yeah, so they really are synchronized, so especially if you, I'll start maybe, in the initial stage, you see they are desynchronized very initially, but then quite soon after, I don't know, 5 hours, so they are now flashing all together. You see, you cannot control it. You see, so you put there. So there is a really extremely noisy oscillator. It's a genetic circuit which is not perfect. So if you follow the periodicity, it is even in one cell, it is not periodic. Moreover, cells divide.
So it's not even Kuramoto at all.
Okay, there is something periodicity. Yeah, no. But I mean, so it's diversity is there, but there also a lot of noise. It's not only diversity in their frequencies, but a lot of noise intrinsic. And there is overlap because cells divide and many such things. And maybe I'll show a more, how to say, spectacular example. So this is the Millennium Bridge in London, which was opened in 2000, pedestrian bridge. And there was a lot of people there. And you will see what happened there. So it is a bridge. There are many pedestrians. Each person is walking with its own pace, so there are not synchronous like army unit. But nevertheless, so there you see, so oscillations appear. You will see this more in details. So you see, so how the bridge started to sway. And this is, okay, so people didn't like it. They immediately closed it after the first opening day. And the reason of this, so there will be some enlargement here. You see, so how it is sways, yeah? So, and this is exactly, okay, and this is exactly this Kuramoto transition. And they started to test it. They added people, this company, in the night, not to attract attention. They sent their employees on this bridge, and they just increased number of the persons, because here the coupling is not divided by n, but it's just proportional to the number of pedestrians on this bridge. And there was a critical number of critical parameter, epsilon, so some 166 person. When it was more on the bridge, it started to sway because the coupling became too strong. And this is exactly so. Each pedestrian is described by some equation for its pace. No, okay, so it's continued to play everything. So let us, okay. So it is exactly this transition. So there is maybe some equation for the bridge, which is a macroscopic oscillator, and there is some maybe several hundred persons on it, which is each some has also periodicity due to steps. And because of this coupling, so they become in phase, and they experience a large force on the bridge, and bridge becomes swaying, and it is self-supporting. So this is example. So they put additional attenuation there, and this shifted so critical parameter to very large values. And so now you can safely go across this bridge. So these are examples of this Kuramoto or this transition in particular systems. It's like transition from this situation to this situation. Yeah, this situation is normal, people walking on the bridge, and this is when this happens. So they go more or less in phase, and the bridge is oscillating. Okay, now, so there is some, how to say, mathematical mystery here, which I cannot say that I completely understand, but somehow it works like following. So Watanabe-Strogatz, they considered the following set of equations. Now here, the number of oscillators are arbitrary, n. So there is even no thermodynamic limit. Just could be 10, could be 5. And they considered, so they considered situation when there is they have all the same frequency. Moreover, you can allow this parameter to change in time arbitrary. And they assume that these oscillators are subject to some common field. At the moment, we don't say that this field is created by oscillators themselves, but it doesn't matter. It's just any function of time h, complex function of time h. So there is just a set of equations. So this is the same equation, for many objects. The only difference is in their initial conditions. Yeah, but they experience the same field, common field. Okay, it's also interesting that there is a problem of how bicycle, so it leads to the same equations, essentially. Okay. And then, so they did the following. So you use some transformation, which is called Möbius transformation. So you introduce, instead of your old phases, you introduce new variables, and you introduce a complex, you use some complex parameter, it's a small z. So this is how Möbius transformation. So there are new angles and new and two complex variables. So it is an overdetermined system. Yeah. So it is a you started with n variables, and now you have n plus 2. N here and 2 in this complex variable. And so you impose two conditions. Or one complex condition. So you assume that these angles satisfy this. So they're centroid, so sum of their phases is 0. You can impose this. Then it is a unique transformation which gives you from old variables new variables. And then it happens so that you just substitute this so that this, okay, it needs some calculation, which, okay, anyhow, difficult to follow, but you end with the following system of equations for these variables. This one complex variable obeys this, where omega and h are just arbitrary functions of time. But the equations for all these new angle variables are the same. You see, so it is the same equation because psi k is not entering here. And this means so that so you have in your original system n minus so 3 integrals or integrals. Because you see, so you can just define one of these angle variables, and you determine all others just by shifting initial conditions. So you have, you describe this one, so you have 3 equations and n minus 3 integrals of motion. And this is independently of what is here. Omega is a function of t, it's not constant, and h. You just, yeah. So the Watanabe-Strogatz says so that the system of phases, at the moment they are not coupled, but it's just they are driven by the same fields. It is a, how to say, we call it partially integrable system. It's only, it has 3, independently on its size, it has 3 non-trivial equations, which are here, and n minus 3 constants of motion. Okay, so this is their theory, how it works. And this is a great reduction, yeah, because so independently of size of your system, you can reduce to 3 equations. Okay, so what is interpretation of these variables? So you have 3 new variables. One is, so you see one is this rho, another is this phase, and another is this alpha. So this is not so important, but these 2 are more or less the size of this bunch of oscillators and its position on the circle. But this small z and this order parameter are not the same. Yeah, you ask, so what is that? So capital Z is what Kuramoto introduced order parameter. And they are not the same. They are more or less proportional, but they are not the same. So it's some kind, you can say, okay, there is some new order parameter, which is this small z, which is due to Watanabe-Strogatz. And it's like this. But this reduction, yeah? It's arbitrary function of time. It's arbitrary function of time. Omega and h are arbitrary functions of time. There is at the moment no coupling, so you can use these equations to describe maybe external forcing on these oscillators, but also you can describe it as a coupling. And I will come next. So if h is due to coupling, so then, but you see, so generalities here even without coupling. It's a little bit, I remember, so you had an old paper about this holographic map and something. It's a little bit resembling, but I could not find real connection. Maybe there is some. Okay, so this, so the only case when it doesn't work, so if it is, if you cannot satisfy this condition, so for example, if your oscillators are already in some clusters, so then you cannot do this. But in most situations, you can perform this transformation. It applies for any n, but it applies only if the right-hand side of the phase dynamic contains first-order harmonics, sine and cosine. So if you have a more general function here, not like this, but something more complex, so it will not work. And if oscillators are identical and identically driven. Yeah, so this is restriction. But if it is so we can apply it to a Kuramoto problem for identical oscillators. So now I say my omega is a constant, it's just, and my h is this. It is a Kuramoto mean field with this. Its equation also belongs to this class if I just write h is like this. Yeah. Now beta is additional phase shift. So if beta is 0, it is standard Kuramoto model. If it is beta, then it is called Kuramoto-Sakaguchi model, but it's minor problem. So you see, so we can reduce this Kuramoto problem to Watanabe-Strogatz equation. The only difficulty is to connect these two order parameters. So the Kuramoto order parameter, which is formulated in terms of initial, so to say, original phases, and this additional parameter which comes into Möbius transformation, which is small, which is this rho e to the I phi. And this is, so there is some expression, but it is just not easy. So this is this function, which is generally you have to, so there is some function, but, and all the constants of motion, which I said, so n-3 constants are coming here, but okay, it's complex function. So it's so in principle it exists, so dynamics can be reduced to low dimensional, but the equations are nasty because what is coming is some kind of complex sum over all integrals of this equation. Now, but there is one simplifying case when you really get you get rid of these constants and such things. Now, if you look how this function gamma looks like, so it can be written as a series where these coefficients are this, how to say, Fourier harmonics, finite Fourier harmonics of these constants. You take these constants of motion, you multiply IL, sum, and this will be your coefficient, CL, and you have infinite sum. And this is, and there can be an important simplifying case. So if all these constants, they vanish. So this is, of course, a very particular case, not general, but if they all are 0, then all the sum disappears, and you have this one and these 2 order parameters, which were here, this Watanabe-Strogatz order parameter and Kuramoto order parameter, they will be equal to each other. It's, of course, a very particular case, but it gives you, so they will be equal. In all other cases, they are different, and you have, but nevertheless, there is a reduction. So it means so that, formally speaking, your dynamical system has n-dimensional dynamical system has n-3 integrals and 3 non-trivial equations. But these equations depend on the values of all the integrals. Yeah? So only in this case, it will be a very simple equation. And I write this equation, so it looks like this, which is, you can simply solve it. Because if you write equation here for the real order parameter, so absolute value of this, you see so that this is just one equation which says you what happens with this order parameter. So if epsilon, so it depends on this product epsilon and cosine beta. So if it is positive, so you will have r equal to 1. And if it is negative, you will have r equal to 0. It will be exactly this transition from, how to say, asynchronous state to synchronous state. In one case, your coupling is repulsive, so it wants to spread oscillators along the circle, and the order parameter will be 0. And another case, it is attractive, and all the phases come together, and it is perfect synchronization. Yeah? So for 2 oscillators, in both cases, attractive and repulsive, we had synchronization, but so it was antiphase. If you have many, you cannot have antiphase, because so you can only arrange them uniformly on the circle, or not uniformly, but at least so that this order parameter vanishes. Okay, yeah. So this, in some sense, solves this problem. Okay, so here it is again written. So essential is also this parameter beta. Attraction is, okay, if epsilon is larger than 0, then you have it's just solution of this simple equation. So reduction works. No, it's a phase is not uniform in this case. It's just its order parameter vanishes. It's just, you see, any configuration will be okay, even like this, yeah? But it means so that its average e to the I phi is 0. So only this condition. No, so because they don't enter. And because here we have all identical oscillators. Yeah, because so if they are, yeah, because if they are all identical and they have the same frequency, so if this term vanishes and they have all the frequency, so this configuration just rotates as a whole, and it is invariant, yeah. Sorry? No, you see, it's nothing is neglected. There is assumed that the coupling is only through this first moment. So that other moments are not, because only in this case this Watanabe-Strogatz is applicable. In other case, you cannot have this reduction. It is maybe I a little bit rearrange my slides, and they now go not to the sum I'll come later to this point. I want to here, sorry for this, it was a lot of here. Okay, now let us come to what is called Ott-Antonsen ansatz. So Ott-Antonsen, they in fact, so I now formulated the same equations, although it was originally somehow different, just to see that this theory by Ott-Antonsen is essentially the same as what we discussed before. They did the following. So let us consider the same model, but in the thermodynamic limit from the beginning. And so we write the following conservation equation for the probability density. Yeah? And then, so we know that this rho is a 2 pi periodic function because it's our variable sleeve on a circle. And so we represent it as a Fourier series. And we write an infinite equation for these Fourier coefficients. So you see, so this is this system of equations for Fourier coefficients of this, of this Liouville equation. Yes. And now, if we rewrite this equation, so this is the equation for the first, and then this for all other. And then Ott-Antonsen realized that if we make such an ansatz, so if we assume in this equation that Wk, so high harmonic, is just the first harmonic in power k, all equations will have the same form. So this, so this equation will look like this, and this is exactly the right-hand side of the first equation. So it means so that this is an invariant manifold. So this, how to say, situation, it is a special situation, but if it is so, then it remains so. And instead of the huge hierarchy of equations, we have just one equation for these Fourier harmonics, which we now call back Kuramoto order parameter, and we have this equation, which is essentially the same as Watanabe-Strogatz. So it is, yeah. So Ott-Antonsen equation is the same of Watanabe-Strogatz, but in one case you immediately start with the thermodynamic limit, look on Liouville equation, and you see so that there is some invariant manifold there on which dynamics is low dimensional. And this is, if you think about constants, so this is exactly corresponds to uniform density of the constants in the Watanabe-Strogatz formulation. And Ott-Antonsen is correspondingly formulated directly in the terms of the Kuramoto order parameter. Yeah. So you see, so there is a still, so there is some arguments that this manifold, what is called Ott-Antonsen manifold, so the special conditions, is somehow attractive. So if you don't start on it, you are attracted to it. But I am not completely, how to say, convinced, so that might be, it's difficult to deal with kinetic equations of this type. It's a little bit resembling of theory of Lassov equation, which as far as I know is very complex. And so here probably is a wide field for mathematical understanding on how this really works. But there is one more step which you can do with Ott-Antonsen equation. Now, so up to now, all oscillators were identical. But real challenge is that if you have non-identical oscillators, you have distribution of them, then the idea is, okay, how you can deal with this. You can say, okay, I have now, so my omega is, has some distribution. It's J of omega. This is natural frequencies of oscillators, and there is some distribution of them. Now I can say, okay, for each particular frequency, I can write Ott-Antonsen equation for oscillators at this frequency for this distribution. But so but I get here parameter omega, so my order parameter depends on this frequency. And my field now should be integral of this local order parameter over this distribution. Yeah? So now to this corresponds some order parameter depending on omega, and then altogether they give the total mean field, which is now doesn't depend on omega, and this is how to say integral z g of omega d omega. Yeah? So, in fact, you reduce the problem to a differential equation with this integral term, so it is integral equation. Yeah? Integral differential equation. Now, it looks like it's a complex situation, but as physicists do, so they want first simplification. You can think, could I somehow simplify this integral? And indeed, Ott-Antonsen realized so that if this function has a Cauchy or Lorentz form, then there is a hope to calculate this integral through residual theorem if so z has no poles in the upper half plane, then you can calculate this integral through residuum like this. And if you, as a physicist, let us assume this, or maybe there are some arguments that this will be true indeed. And then, instead of these all equations, you get just one equation for the order parameter of this type. Now, for non-homogeneous population, but with very specific Lorentzian form or Cauchy form. So you just get one equation for the complex order parameter. It's time derivative, so there is a mean frequency. Here, minus delta states is the width of this distribution. And here, there is a coupling term. So you see, so there was many assumptions. So assumption of Ott-Antonsen manifold and assumption about this analyticity. But at the end of the day, you get one complex equation for your complex order parameter, not in the steady state, but with full time evolution. And you can look, so it is just as nicely, it is just as equation for one oscillator. Because so it has some constant amplitude depending on epsilon. And this is exactly what we saw as a Hopf normal form or Landau-Stewart or Poincaré oscillator. Yeah. So this is how this, and now, so to say, physicists are happy with this, so because they now can generalize this, because you have the whole population is reduced to one equation for one complex order parameter. Okay, so for example, what physicists could do and what we particularly do. So now you can generalize this. You can say, okay, suppose I have several such populations which are somehow coupled with each other. Then each population, I can write equation for the complex order parameter. It will be my effective dynamics. And I can couple them, and I can consider, so to say, on the higher level, so that my many populations of oscillators are described by just system of ordinary differential equations, instead of writing all densities and such things. So you can just do this. So we did this with Komarov and others. And okay, so there is some complex, could be dynamics, but it's just a finite dimensional dynamical system, which you can apply. So just, okay, steady states, orbits, whatever you want. For example, here you can, if you can have 3 populations with different mean frequencies, and if they are in this resonance, then you get a system of 3 coupled equations for 3 order parameters with such coupling terms. So it's maybe not so interesting, but it's just physicists play with this. For example, one of typical examples is that if you have population not of this type, but something like this, with 2 maxima. So then you represent it as a superposition of 2 Lorentzians. And for each of them, you write Ott-Antonsen equation, just one oscillator, and then you have this coupled equation. You can analyze this. If you want to put some external force, you can also do this. Yeah, so this is really, so people are so happy so that they really follow this approach. Okay, now maybe I try to, okay, look, okay. I'll go back. Okay, so there is one interesting phenomena which can also describe with this Ott-Antonsen approach. So here it is what I said in general form. So for each you write Watanabe-Strogatz equations, for example, and then couple them. And there is an interesting phenomenon which is now popular very much in physical literature, which is called chimera state. This is this picture. So it was an original paper by Kuramoto in 2002. There is a funny journal published in Minsk in Belarus about nonlinear science, a very local journal, and they published proceedings of some conference where, and Kuramoto and Bataktok submitted their paper to these proceedings, and it's published in this journal. So it looks like its paper is online, but it doesn't have DOI number, DOI. So it is very difficult. So you start citing it, but the normal journals like Physical Review, so they say that probably this article doesn't exist because it doesn't have DOI number. Okay, so but it really exists. Probably it's more cited than all other papers in this journal ever. But it was an interesting paper. So what they did, so you see, Kuramoto model is a model with global coupling. So you take, you sum field from all oscillators, and on all oscillators act the same field. Now, what they did in this paper, they really considered a spatial extended situation. So it's oscillators along this x coordinate. And the coupling is not global. You don't sum on all, but you just put a kernel function, exponential. Here should be minus, I suppose, yeah? Okay, and you sum from the neighborhood the field with this kernel function, yeah? So it is some kind, it's intermediate between completely local coupling and global coupling. So it is exponential kernel. And they observed such a pattern. And otherwise, all oscillators are identical. And they observed such a pattern. So you see, so here, all oscillators have the same phases. It's just one snapshot of the phases. And here, they are scattered. So here, oscillators in this region and in this region, they're synchronized. And in the middle of this picture, they're desynchronized. OK, not completely desynchronized. So order parameter here is not 0, but it is not 1. So it is, there is some large density here, you see, but here smaller density. Yeah. So there is some kind of symmetry breaking. So instead of having everywhere synchronous state, you have part of your system synchronous and part asynchronous. And it was somehow, OK, not really mentioned unless Steve Strogatz, and with his student Abrams, they start to look at this more carefully, and they ended with the simplest situation where the synchrony and asynchrony coexist. And this situation is not of this one-dimensional medium, but just of two populations. There are two identical populations, A and B, and which are coupling inside, just usual Kuramoto coupling. But they also are coupling with others, but with this different. So there is a minimal, how to say, asymmetry in the system, so that inside you are coupling stronger and across you are coupling maybe weaker. So there are two such populations, and they what they observed is the following state that, but otherwise it is fully symmetric, and they observed that one is synchronized and another is asynchronous. So such states where one is synchronized and another asynchronous. So this is probably the simplest setup for chimera. And they also coined this term because Strogatz is an experienced guy, so he knows how to attract attention to get cited. And so they wrote in this paper, not in the original by Kuramoto, but Akto, that, OK, so chimera is something which combines from different animals, so uncomparable things. So, for example, so lion and angles or whatever. OK, so but now in this simple situation, you can even make experiments. So, for example, in this group around Showalter, they took 40 chemical oscillators, and they coupled them according to this scheme. And they observed that one group was synchronized and another was asynchronous. Indeed. And even more spectacular experiment was with these metronomes. So it is a group around Erich Martens in Göttingen. They took two platforms. On each of them, they put 16 metronomes, and these two platforms were additionally coupled. So they are somehow coupled inside, but also this coupled to this a little bit differently. But otherwise, this is symmetric. And they observed, OK, so it's very hard to see here, that in one, so to say, group, they were synchronous, and in another were asynchronous. So it's formally speaking, so these equations for this situation are just two coupled sets of, say, Watanabe-Strogatz equations, because inside they are all identical. It's Watanabe-Strogatz or Ott-Antonsen. And then you have two coupled equations. You can look for bifurcation there, and you can find symmetric and asymmetric solutions. And this will be Okay, we'll describe these observations. Okay, so this is about chimera. It's really, so if you look on physical literature, it's exploding number of papers, so people in different situations look on this and try to find. And in many cases, so you describe this really with the Ott-Antonsen and Watanabe-Strogatz. Yeah. So we have some 20 minutes. Maybe I'll not use them full. I want maybe to describe two effects, so which we looked at, and I think it's quite interesting. And okay, yeah.
From this Ott-Antonsen argument, it doesn't seem that the distribution of days.
Yes. You cannot do with Gaussian or something like this. You need something which has really allows you to apply this residual theorem. So you see, so you need to calculate this integral. You see, so you have this set of equations. Now, if it is general J, okay, so there is some integral here. What can you do else? Now, it's only in the case of this, or maybe, okay, if you have this two, you have more poles, yeah? If you have just finite number of poles, so then this integral will be just values of this, of your function at some points at complex plane. So then you cannot do better than this equation. You can try to find steady states or in some, how to say, consistency or whatever, yeah? Okay, so you can do linear analysis of stability of the state, say z equal to 0. This you can do. So make linear stability analysis. So then you see, but this is, yeah, then you can linearize and then you can say, okay, so instability is related to the value of this G at maximum. So there is some formula for instability. Okay, so it is, it always, typically always is synchronization transition if coupling is strong enough. It's only, could be second order, first order, it could be different. But you don't, you see, you can solve, how to say, self-consistent equation for stationary state like you do in the Curie-Weiss theory of magnetism. So you write self-consistent equation for magnetization. But you don't get real dynamical equation for your order parameter. You can find, suppose I have some order parameter, under which condition. And here, it is you get just a dynamical equation. So this is, otherwise you have some self-consistency condition in the integral form. Say for Gaussian, if you use Gaussian or any other. Okay, yeah? No, sorry, go in wrong direction. Huh? Here. Okay, so it's formally speaking, it's better to write this kernel, so not as exponential, but through the cosine hyperbolicus, so that here it is a so there is a, okay, somehow they used non-smooth, non-smooth boundary condition, but you can smoothen it writing kernel function which has zero derivative. So it is really smooth periodic function on the circle. So it is periodic boundary conditions here, and the kernel should satisfy them. Such kernel.
But none of it have synchronization.
Oh, but it's all periodic in space. I mean, you have homogeneous synchronous. No, why it is reason why it is here? No, it is just because initial conditions. So this piece could be everywhere. Sorry, it's just because they considered some. They started with symmetric initial conditions, so it evolved into symmetric pattern. But this could be anywhere. So there is no any. Yeah. Sorry? No, okay. So there is, if you make a theory, so you typically write equations in the integral form and such things. Now, if you make numerical simulations, so here maybe 1,000 oscillators, you observe this. Now, there was a paper, Wolfram and Amelchenko, they looked really how far you can reduce the number of oscillators in this situation. And they found that if the number of oscillators is really small, then the lifetime of this, so then the state doesn't live infinite time, but it lives finite time. It's like a little bit like the stable chaos. So then you, after very asymptotic time, you end up into synchronous state, but this time exponentially depends with number of oscillators. So if you have 1,000, you in practical times never observe this. Yeah, in PDE, it's just pattern formation problem. So you write a PDE of the, we did it, so it's you write a PDE for Ott-Antonsen, you have something like complex Ginzburg-Landau equation, PDE, and you look, so what are possible periodic patterns there, and you find such patterns. So it is some kind of non-trivial pattern. You can say, okay, it is a pattern formation for the order parameter. Yeah. Now, I maybe want shortly to discuss one problem which is quite overseen in this field when you write Kuramoto equation. Now you see, synchronization phenomenon is a nonlinear phenomenon. Yeah? So because the basic equation, it's Adler equation or Kuramoto equation, is already nonlinear because it contains sinus, because it is written for a variable phase for which you need to have equations which are 2π periodic. So you cannot have linear equation. But nevertheless, Kuramoto model, it has some properties of, I would say, not of linearity, but of superposition, of linear superposition. Because when you formulate the Kuramoto model, say in the beginning, I'll put here these equations, yeah? So you just write here a sum of contributions of pairwise interactions. Yeah? So it means so that there is no any, how to say, so it is like superposition. So interaction of two oscillators, and so of one with 2 and one with 3, they don't affect each other. You just sum them linearly. Yeah? It's superposition principle. But it must be not necessarily so. And this here I come to this possible generalization. In the Kuramoto model, some kind of linearity with respect to forcing is assumed. So you have an oscillator, and on oscillator X are acting force 1, force 2, force 3. And indeed, in the first approximation, you assume so that you have one term from this force plus one term from this force, but there are no terms which are proportional to epsilon 1 multiplied with epsilon 2. Yeah? So these terms are not in the Kuramoto model. You assume superposition principle. And, but this is not necessarily, because if you just have one force, you can have epsilon, epsilon square, and so on here. And this will mean so that you mix different terms. And for example, you can imagine the following situation. Just think about this Millennium Bridge. Yeah? You have many pedestrians, and suppose they're not taking hands of each other, they interact only through the motion of the bridge. But now, for this motion of the bridge, probably a linear oscillator is a good approximation. But maybe if it would be not a Millennium Bridge, but some bridge in the mountains, which really has a long way, so maybe these oscillations will be themselves nonlinear. So this means so that you have many individual oscillators, but they are coupled through some nonlinear unit. Why not? Yeah, so you can put it. And this will mean so that you cannot write here your coupling just as a superposition, because in this nonlinear unit, all these terms will be mixed, and there will be nonlinear combinational terms. So unfortunately, I don't know. I thought a lot about this. So it's a little bit like multi-spin interaction in the statistical physics. But in fact, so these main effects which are here, I could not find a good equilibrium analog, so some kind of Hamiltonian, like this. But in this field, you can easily implement this because you are not restricted to a Hamiltonian structure of the equations. And this means so that your H is not just proportional to Z, but it could be your field, could be some nonlinear function of order parameter. Yeah? So it means so this would be nonlinear coupling in this sense. So that you not have just Z here order parameter, but nonlinear function of the order parameter. And for example, you can put here, okay, so there are some examples, but you can you can make in such a way this nonlinear function that, for example, for small coupling, you have attractive interaction, but if your mean field is large, it will be repulsing one. Yeah? So suppose, so if you're coupling between spins, so if magnetization is small, it is ferromagnetic. But if magnetization is large, it becomes antiferromagnetic. I could not find any Hamiltonian model for this, but here you can really realize this even experimentally. It will mean following, so that small coupling tends to synchronize them, but if the mean field becomes large, they begin to repulse. So you will stay somewhere in between. So you will not fully synchronize, because then you are repulsive, but fully desynchronize either, because there you are attracting. So it will be some kind of partial synchrony which can come from this situation. And indeed, so our colleagues somewhere here would be, sorry for this. So this is somehow how it's called, how it looks in experiment with electronic oscillators. So here it is usual Kuramoto linear coupling. So these are real experiment with electronic oscillators, I suppose around 80 of them. So you see, so their frequencies come together and they become synchronized. Okay, frequency also changes, but they're really, so here there is synchronization because all the frequencies are the same. And here it is nonlinear coupling. So if the coupling is small, they tend to synchronize, but then If it is large, so then they again go away, but the mean field somehow remains relatively large here still. So you see, so it could be some models beyond this traditional Kuramoto, which can appear in such situations. Maybe as a last, maybe complication, I will say the following. So in all this Watanabe-Strogatz theory and Ott-Antonsen theory, and also in this example, it was really assumed that the coupling is pure sine or cosine function. So it is just first harmonic, so e to the I phi is coming. Yeah? But this is somehow special case. So generally, you assume that your coupling can have such term plus maybe with some coefficient e to 2 phi plus some coefficient e to I 3 phi and so on. Yeah. So it's more general. And then it's all this Ott-Antonsen theory breaks and Watanabe-Strogatz also breaks. Now you can ask whether there is some real theory breaks, but maybe the phenomena are the same. But it's still, so there are some new things appear in such, if you have more harmonics, especially if they are not just some small corrections, but if they are of the same size. And maybe this will be my last couple of slides. Yeah, here. You see, so if you have a coupling which is sine plus sine of 2, yeah, so you have two such terms. Then if you draw your coupling function, or it's also a so-called XY model with nematic coupling, ferromagnetic and nematic. You can have such a situation so that your coupling function has two branches. So if you add sine and cosine, so you have some mean field, but you don't know where your oscillator has a choice, either to sit here or to sit here. You see? So each oscillator in such mean field can sit here or sit here. And you have arbitrariness of this. So you have a so-called multi-branch entrainment, and you have multiplicity of states. Say, compared to this case, when this second harmonic is small and you have only one branch, it is really looks like sine, but maybe distorted, and here it is something different. And this leads to some phenomena which we still don't understand. So we observe states which seemingly don't appear due to any, so to say, bifurcation from the instability of asynchronous state and such things. So I tried to summarize so what is basic things which are known for ensembles. There are striking examples of real reduction of the dynamics to low-dimensional situations due to Watanabe-Strogatz and Ott-Antonsen. In many cases, they really can describe many phenomena, including maybe cases of nonlinear coupling, external noise, nonlinear, yeah, and other types of forcing. There is a life also beyond this, like this example shows. And I would say so that as far as I know, real mathematical results where Bastien Fernandez working and also other people, so they're still not covering this full what, say, physicists do, but there is, in my opinion, very interesting field of collective dynamics. So at this point, I thank you. maybe small announcement what I want to describe on Friday. So today it was mainly on oscillators. So really on periodic oscillators, so few of them, 2 and many. And then I will will devote some part to oscillatory media, so say lattices, and then on other types of synchronization of chaos due to coupling and external force. Yeah, so something more in this direction. Mm-hmm.